All right, Calculus 2, welcome back. We're going to head into 7.2 here, the volume of a solid of revolution. So we've learned so far we can use an integration to get area under a curve. Then we started doing area between two curves. We're going to use integration to get the volume of a solid of revolution. So that's a little different. I'm going to try to explain it to you. Let me start with this idea. If I have a cylinder, that's a cylinder. You know the volume of a cylinder, I hope. It's really easy because it's the area of the base. Pi r squared is a circular base, pi r squared, and then you multiply by the height. So it's got a radius r, it's got a height h, and I'm saying it's the pi r squared, it's the area of the circular base multiplied by how high it is, makes it volume. Okay, what if it was turned sideways? Same thing. You just might not call that height, maybe you'd call that length, but it's pi r squared times the length or the height. And what if it was really, here's what I really want to do, is actually sort of turn it sideways and make it very thin. Make it very thin. And then it's still got a radius, so the volume is still pi r squared times its thickness, which we could still call h. Okay, I'm not changing the formula, but I'm just suggesting that this is a thin disk. What I'm going to teach you about is called the disk method, and this is the volume of a disk. So let's go over here. So those are easy ideas, just building up to this idea. The volume of a solid of revolution. So, to get volume, you have to have a 3D figure. This is a two-dimensional figure. We call it a region in the XY plane. But what we do then is we revolve it around some axis. So we take this two-dimensional region and revolve it around the x-axis. In this example, we'll do a lot of different axes. And here's my little notation. I do this little, it's kind of a subtle little notation, but that means I'm revolving it around the x-axis. I could write the phrase, revolve it around the x-axis. So now you have this two-dimensional shape, and you have to imagine it being revolved around the x-axis, which creates a 3D shape, and we can find the volume with what's called the disk method. And it's this idea. Now, I'm saying you have to imagine the 3D shape. You could attempt to draw it. Sometimes, I'm going to draw it now for you. It's when this revolves around, this end will look like this. Well, kind of tough to draw. This end will look like this, something like this. And this will look like this. So there it is. I'm revolving it, and it's a three-dimensional shape. And what I do is, like we used to slice area into a bunch of rectangles and add them up, I'm going to slice this into a bunch of circular discs and add them up. So let's just look at one representative disk. So there's a thin little disk. There's a whole stack of them lined up there. But here's a thin little disk. And to get the volume of that thin little disk, this one particular disk, I'm going to do pi r squared. Now what's r? The radius of the disk is this. That's the radius of my disk. And what is that? From the x-axis up, it hits the function. It's that y value when you hit the function. That y value when you hit the function is the function. So it's pi, and it's the function squared. So my radius is not a number, like it was over here. My radius is a variable. My radius changes. My radius is this function. So right there, the radius is the function. Over here, it's the function. Over here, it's the function. And that function is changing. So it's the radius squared. And then I need to multiply by the thickness. Hang on, pi r squared. And then I need to multiply by how thick that disk is. Now you remember, we're doing area. We have our little rectangles. Remember how thick they were? Delta x Of course, when they're really, really thin, when you let delta x go to 0, it's dx. So I'm saying the thickness of this, sort of the height of this, the thickness of this, is dx. And then we add all that up. So to get the volume, we do an integral of pi f of x, the function is my radius, squared dx is my thickness. And I add up all those little disks from A to B. I hope that made sense. It makes sense to me. Maybe you have to watch this a couple of times. So, I'm going to get rid of this picture. Officially, what we're talking about here is the disk method for finding volume. And the way it's presented in the book, I mean, I went through that idea with you with that thing called f of x, but the way it's presented in the book is the volume is pi. They pull the pi out in front of the integral. Pi is a constant. You can pull it out in front of the integral. You have an integral from A to B, and they call it r of x. They call that function, because it's a radius squared. So they just call the function r of x. You're looking for your radius. The radius is usually the function, but sometimes it changes. It's not always that function. We got more advanced examples. Okay, so there's the official formula for the disk method. Now the truth is, that's the disk method. This is the official formula when you're going around a horizontal axis, like the x-axis. You know, there's another formula. I'm going to draw another picture. I'm going to get rid of this. If somebody said, let's spin this region, we got a region here bounded by C and D, and they said, let's spin this region around the y-axis, then you create these disks going around the y-axis. That's a two-dimensional region now spun around the y-axis, creates a three-dimensional region. We can find the volume, but what's the thickness of my disk now? The thickness of my disk now is dy, so you would do the whole problem in y's. The radius of your disk would be that distance x. That distance x hits that function of y. This is how we talk. It gets a little confusing, but you can work in y's if you're going around the y-axis. And so that would be pi, that would be r of y squared dy is the thickness of the disk. Remember, it's pi r squared times the little thickness of each disk. Then you add up millions of little disks from C to D. So that's the formula if you're going around a vertical axis, like the y-axis. So we get confused here. There you go. That's the disk method presented. We probably should do an example. I want to bring up one thing. And I won't do an example of this, but well, if the disk has a hole in it, there's some volume you want to subtract away, then the book calls it the washer method. To me, it's not really a new method. It's the disk method with a hole in it. You have to, if there's a hole in it, let me show you a picture of that. You had this kind of a picture. You had some function here, let's call it big capital R of x, some little function here, R of x, and you spin this around the x-axis. But this is the region, and you spin it around the x-axis, then there's this shape, but there's a big hole in it. You don't want that volume. You just want the volume of where the region creates volume. You don't want the volume of this inner hole. So, like I said, it's the disk method with a hole in it. You want to subtract out that inner volume. The book calls it a washer method. That's okay. But it all of a sudden turns into this formula. Pi. And you do the outer function squared minus the inner function squared. I mean, you're just doing the volume of the outer disk minus the volume of the inner disk, the hole you don't want. I hope that makes sense to you. from A to B. Guess what? There's another version of the washer method in Y, so the same thing in Y's if you're going around a vertical axis. So we'll do all kinds of examples coming up with all that. So this is just sort of the first presentation, and before it's over, let's do one little nice example. So again, I'm going to get rid of that picture, okay? I'm going to get rid of that picture, and I'm going to say this. I'm going to say it, instead of writing it, I'm going to say, find the volume of the solid formed by revolving the region, and the region is defined like this. The region is bounded by y equals the square root of x, y equals 0, and x equals 4. That's a region, that's a two-dimensional region. We practiced a lot of that in 7-1 when we were trying to find the area of it. Now we're going to take that region and spin it around, and we have to say revolve it around the y-axis or the x-axis or maybe some other horizontal line or maybe some other vertical line. We'll get more advanced as we go. But let's just do this around the x-axis. Around the x-axis. So this is a simple example, okay? And maybe I need a picture of it. I'm going to help you with a picture of it. The picture helps. I always try to draw these pictures. Y equals the square root of x is this function. Y equals 0 is this. And x equals 4 is a vertical line over here at x equals 4. See, what I'm giving you is the boundaries of the region. So there's the boundaries of the region, and then what are we doing with that region? We're spinning it around the x-axis. As this spins around the x-axis, maybe you can imagine the shape. You don't really have to draw the shape. What you really need is the radius of the disk. We're going to slice it into 1,000,000 little disks, and I need the radius of one representative disk. Hey, do you think there's a hole in this region, this solid? Do you think there's a hole in it and I have to use the washer method and I have to subtract out the inner volume? No, I think this sits right on the x-axis and you spin it around. There's no hole in this. There's a nice, it's a solid without a hole in it. No need for the washer method. All I got to do is set up an integral, pi out front. I'm going to call this volume, and I need the radius of my disk. I mean, here's an example of a disk, and here's the radius of the disk. The radius of the disk is the function. The function is the square root of x, and I need to square it because it's the radius squared, dx. I'm going to do that for a bunch of little disks as they move from 0 to 4. I'm doing that for a bunch of little disks as they move from 0 to 4. That's easy. That's an easy example. You have to learn to look at these pictures and set up this integral. I'd like you to memorize these formulas. I think if you understand the geometry behind these formulas, they're easy to memorize. Okay, let's just finish this one real quick. It's easy. When you square the square root, you get an x, but you haven't integrated yet. When you integrate, you get an x squared over 2. You're going to evaluate from 0 to 4. Don't forget, there's a pi out front, so there's a multiplied pi out front. But you with me? That was pretty easy. Square the function, integrate it. Now let's evaluate it. You plug in the 4, you get 16 over 2. That's 8 pi. You plug in the 0, you get a 0. I'm finished. The volume is 8 pi. We don't really have any units, you know, when we do these math problems. It is units cubed. If the x-axis and the y-axis was measured in inches, this would be inches cubed. But we kind of do have it. We don't bother with the units unless we do a real application. So these math problems are kind of unitless problems, but it is whatever units they are, units cubed. It's a volume. All right, that was fun. There's plenty more to do. A lot of good homework here in 7-2. So good luck.